Hello everyone and welcome. My name is Gyula Sallai and I will be talking about how we can use LLVM in a model checking workflow. Well, first of all, why do we actually want to do this? Well, nowadays we are surrounded by different embedded software systems. Many of them are written in C, and these are present in almost every aspect of our lives. We have them in our home appliances, washing machines, microwaves, cars, etc. And of course, as with everything, we want to have an increased confidence in their correct behavior. Such confidence can be obtained by using testing methods or static analysis, and next to those, we have the technique known as model checking, which uses mathematical constructs and formalisms to reason about certain properties of a system. Model checking requires two things: a formal model, which describes our system, and a formal property, something we wish to prove about that system. As an example, if we have a simple traffic light, we could have its formal model in a form of some transition system, which shows its possible states, and its possible transitions, of course, and a formal property could be something along the lines of, for example, we do not want the traffic light to be red and green at the same time. When we have these two, we feed them to a model checking engine, which can either tell us that, all right, the property can be proven, or it can give us a counterexample, some refutation, which tells us why this particular property cannot be proven. Now, we not only want to do model checking, but we want to do software model checking, which means that what we want to do is to have our formal model built up automatically from the already implemented source code. So basically, what we want again is that a workflow where we have C code at the beginning, then we have an automatic transformation to a formal model suitable for imperative programs, and also we want to derive the formal property automatically also. As an example, something along the lines of that we do not want some erroneous state to be reachable. Then we can continue model checking as usual. However, model checking is a computationally really hard problem. To be honest, it's undecidable in general, and even for instances where it terminates, it runs on an exponential time or even beyond, depending on the model size and complexity. Therefore, it's rather crucial that we reduce these metrics as much as possible. Therefore, we have two tasks: transformation to formal models and size reduction or complexity reduction in the resulting model. As the talk title suggests, we wish to use LLVM for this purpose. LLVM IR is a suitable frontend for formal verification, not only because it's widely used, but also it's language agnostic, which means that if we wish to add support for a new dialective C or say a completely new programming language, then we can do this a little bit more easily using LLVM. Also, LLVM comes with a rich optimization infrastructure, which can of course be utilized for the purpose of size reductions. Therefore, again, what we want to have is a workflow which is able to utilize LLVM for these tasks. So, once again, we have our input languages, we compile them to LLVM IR with Clang, for example, we perform some optimizations on it, then we transform it to a formal model, which is then fed to a verification backend. Our current verification backend is the model checking framework called theta. All right, so how does the transformation to formal models work? First, what we need to have is a suitable formal model for imperative programs. Such model could be the control flow automaton, which is rather similar to the control flow graph. The main difference is that in a control flow automaton, nodes or locations represent possible program counter values, edges still represent control flow, but the operations are present on the edges, and they get executed when control jumps from one location to the other. As an example, if we have this it's rather small, but if we have this summarizing program, then its corresponding control flow automaton could be the one shown on the other side. As you can see, we have our operations on the edges. Also note that we do not have branch instructions, instead branch conditions became edge guards, and also pay special attention to the location called error, which will be used to represent failing assertions of a well, computer program, more specifically a C program. Therefore, what we will have is a suitable formal property when we say that, all right, we do not want error to be reachable in this automaton. However, there's a gap between the IR and the formal models. That mostly comes from the fact that LLVM is, of course, designed for program transformations and eventual compilation. However, the formal models are designed to be front ends for theorem provers. This causes that the LLVM IR has a much larger expressive power. As an example, while SSA form and phi nodes are an essential part of the LLVM IR, they are not present in formal models, so we need to use special transformation rules to solve this problem. Also, a formal model does not have support for pointers or any advanced memory operations. For this purpose, we are going to utilize the theory of arrays, and we are going to calculate integer addresses and offsets over them. Also, the CFA formalism of theta does not support global variables, so we need to promote them to locals where this is possible and applicable. And furthermore, the CFA formalism does not have support for procedure calls. For this purpose, what we need to have is we can either inline them if we can, or replace them with a non-deterministic assignment. So, how does a transformation take place? First of all, consider the program on the left side of the slide. And it's a really simple program with one call instruction, a diverging code path, and an eventual merging point. What we will do is we are going to introduce two locations for each basic block in the program. One location represents the block's entry point, one location represents its exit point, and we will have a single sequential edge between those locations. And of course, this edge will be labeled with the operations of the block. Now, as for BB0, you can see we have two locations. Also, you can see that we have the call instruction on the edge in some form, but for read-like instructions, inlining is actually maybe not possible or not really applicable because, well, we can model read instructions or read operations with non-deterministic assignments. Here we call our non-deterministic assignment havoc. And as for branches, of course, branch conditions became edge guards. All right, then we can continue the transformation as usual. Then we also have the problem of the merging point. Of course, this can be solved by placing the corresponding assignments of the phi node on the incoming edges of the merging point. And of course, this will be semantically equivalent to the effects of the phi node. Now, also, we need certain size reductions. So we are going to use optimization algorithms for that. Our past experiences show that different programs require different optimization algorithms to be able to perform better in a model checking verification process. So what we need to have is a configurable set of optimizations we wish to use, some of which are going to be the optimizations already present in LLVM, mostly the scalar ones like constant propagation, DCE or CFG simplification, etc. Also function inlining for the purposes stated before. And some other transformations which can actually change the program behavior a little bit, such as promotion of globals to locals, where we can do this, and the technique known as program slicing. It's an aggressive size reduction technique which changes program behavior because it chops up a single program into several smaller verifiable slices. By the definition, a program slice is a subprogram which produces the same output and assigns the same values to a given set of variables at a given location as the original program. We pair this given set of locations and given set of variables and given location into one entity called the slice criterion, and this will be the basis of our slicing. As an example, if we have this summarizing program again, its possible slice could be the one shown on the other side if our criterion was that we are interested in the value of variable I at statement 5. Our slicing criteria are going to be assert instructions in the programs, so we will have many small slices for each assertion of the program. So, For evaluation reasons, what did we use to evaluate our workflow? Well, we used the task suite of the competition and software verification task suite, which contains verification tasks written in C, and it has several program categories. Currently, we are only focusing 3 of them. Locks, which describes simple locking mechanisms. ECA, as in event condition action. This describes larger event-driven systems. And SSH, which contains simplified parts of SSH protocol implementations. All right. So the evaluation results are shown in this table. You can see that we have, all right, the model name, variable count, and location metrics. These are just some models, some representative models, because within a given category, we do not have that much of deviation. So, and the opt suffix in a column means that these metrics are obtained using LLVM's scalar optimization passes. The slice suffix shows the results obtained using program slicing. And the hashmark slice column shows how many slices we were able to extract from the program. What's interesting to see is that, for example, for locks, we have many assertions in a single file, so we were able to extract several smaller slices. And these smaller slices had a rather great average reduction. For ECA, we see that the scalar optimizations have rather good effects, and we achieved even more reduction using program slicing. And the same goes for SSH, which also had some significant reduction, almost 50%. Now, for runtimes, what we had is that locks can be verified rather quickly with the verification backend. Sadly, ECA and SSH does not scale that well, so we were not able to obtain practical verification times just yet. So, what did I talk about today? I gave a really brief introduction to software model checking. I also described our LLVM IR-based model checking workflow, which, of course, requires the transformation of the IR to formal models. Also described our approach to a configurable optimization workflow. And also, I just described program slicing for you. In the future, what we are planning to add is an advanced and improved pointer support with a more fine-grained memory model. And also, we wish to introduce new slicing methods, some of which are based on certain heuristics, or some of which change program behavior even a little bit more to achieve a greater reduction. And thank you for your attention.
Okay, we have plenty of time for questions. You're very close, so that's very convenient.
Yeah, thanks for the talk. LLVM IR has a lot of places where some parts of its behavior is underspecified. So in those cases, what did you do?
Well, what we do is just we replace them with non-deterministic assignments, like the havoc you see on the slide.
Okay. And second question, did you have for real C code, do you have like a model of a C standard library as well?
No, we are not there yet.
Okay. Okay, thanks.
Hi. Do you do any kind of bound analysis in your programs? For instance, I know ECA programs are massive and with, I don't know, thousands of unwindings to find the bug. Do you do any kind of bounded model checking?
You are asking for...
If you do any kind of bounded model checking in your program, or just analyze them?
Bounded model checking as the BMC algorithm, right?
Yeah.
Okay, we do not. We use the Sager-based approach.
Okay. And did you apply your technique to all of SVComp benchmarks? Because there are like 9,000 benchmarks there. So.
Yeah, there are quite a lot of them. Of course, it's planned. We are planning to.
Right.
But currently, the verification backend is it's still in development. So there are certain places where it lags, and there are certain places where the front end lags. So
All right.
both need to get up to speed for this purpose.
All right. Thanks.
Hi. How do you generate this LLVM IR? Do you use Clang or some other front end, or do you have a custom front end, or did you modify Clang at all?
We are using Clang.
Just any custom patches or complete standard Clang?
Just standard Clang.
Okay, great. Thank you.
So when translating C code to IR code, Clang has some assumptions built in, made decisions on the semantics, for example. Did you do anything in order to make your verification more applicable to general C?
I'm sorry, I don't really understand the question. So you're asking if some certain... No, what did you ask? Sorry.
You're starting your verification passes on the IR level.
Yes.
But C is not expressed in terms, it's not defined in terms of LLVM intermediate representation. And already Clang, when it translates from C to IR, made some decisions, for example, on the address space or how to translate pointer arithmetics. And you are, by starting at the IR level, you're taking all those assumptions in your model checking too.
Yes,
Did you do anything to avoid that effect and make it more generally applicable to all C compilers?
Well, that's a food for thought. Thank you.
So I think we have time for one more question, but while I run over there, just the question I asked to anyone doing verification: have you found any bugs in real-world code using your techniques?
Not yet.
Thank you. For the SV comp benchmarks that you tried on, so in particular, I'm interested in the LOX benchmark. Did you compare your results both for runtime and memory usage with existing SV comp entries that have participated in the competition in the past?
Not yet, because currently we are mainly focusing on flexibility rather than runtime and consumption. So basically, what we wish to have is more on the preprocessing level on size metrics. So this is what we actually want to have results in, rather than memory consumption and verification time, at first, of course.
Okay, thank you very much.
Thank you.